Yeah there. Today we are going to solve another LeetCode problem named Search a 2D Matrix. A medium level, and it goes like this. You are given an MXN integer matrix with the following two properties. First, each row is sorted in a non-decreasing order, and second, the first integer of each row is greater than the last integer of the previous row. And given an integer target, return true if target is in matrix or false otherwise. You must write a solution in a time complexity of big O notation for log of m multiplied by n. There are some examples here. So here is our sorted matrix, and if we are looking for number 3, then here it is at first row second position, and the output is true. And if you are looking for number 13, it's not in the matrix, and the output is false. There are some constraints over here. The most important one is that both number of columns and rows in the matrix is greater or equal to 1. So the matrix is at least not empty. All right, let's start to work on our code. As you could understand, we are going to do double search. First, we are going to look for a potential row which could contain the target, and then we are going to look for a position of our target in this row. If both of these values could be found, then we are returning true. Otherwise, we are returning false. As both of these entities, I mean values in the rows and rows themselves, are sorted, then we could use optimized versions of search, like binary search, and fulfill our complexity requirements as a result. So let's implement a very abstract method to do the binary search for an integer. So it's going to return an integer type, but it's going to be optional because the search could fail and there couldn't be the result for some kind of arguments. So what we are going to provide as an argument, it's going to be a range of integers to look for. It could be either columns or rows, so high and low values. And also, as it is very abstract version of the binary search, we need to provide the condition checker for some particular values. So if we are talking about the sorted arrays, the values, the integers, could be either too big, too small, or exactly the ones which we are looking for. So let's provide a condition checker, like check value closure, which is going to check the integers, and the result of it, as I said, should be something like too big, too small, or the one. So let's create our own type for that. It's going to be based on enumerations, and we could name it something like compare result. And here we are going to provide all our cases, like too big, too small, and finally, if it is exactly the value which we are looking for, let's name it just OK. All right, so the check value argument is this condition checker, which returns this exact type. As we are starting our binary search, let's check the boundaries first, starting with the low value. So we're going to check value for low and then do the switch. We are going to check for all three cases over here. So if it is exactly the value which we're looking for, then we could return the low value as a result of the method. If the value is too large, then the whole binary search is meaningless in this range, because even the lowest value is too big for that. So let's return a nil. If it is too small, then it's kind of expected state, and we are going to just break the switch and move to the next step, which is going to be, of course, checking the high value. So if the value is exactly which we are looking for, we are going to return it straightforward. If the value is too small, then again, the whole search is meaningless in this case. Even the greatest value is too small, so we are going to return nil. Otherwise, we are going to do the break for this switch and continue. So from this point, we have the range, and we know that both of the boundaries are not the values which we are looking for. And well, we are going to check for the middle value in the range, if it is exactly what we are looking for, or if it is too big or too small. If it is too big or too small, then we are going to shrink the range from one side or another and continue to do this in some kind of loop, right? So for that, we need a movable boundaries. So let's create the mutable versions of our low and high values and name them simply as low value and high value. All right. And finally, let's start our loop. So we are going to shrink our range till the point when the high value stays just next to the low value. After that, there is no value in the middle, so we could stop the search. So while high value is not equal to low value +1, we are going to proceed. At each step, we are going to check the middle value, which could be calculated as the average between low value and high value. And now we could check this middle value using our condition checker. All right. So if it is exactly the value which we are looking for, then we are going to return it straight away. If it is too big, then we actually are able to replace our high value with the middle value, shrink this range, and continue. And we could do the opposite. If the middle value is too small, then the lowest value could be replaced with the middle range, with the middle value. Sorry, I have some misspelling over here. So we are replacing the high value with the middle value over here, and low value with the middle value over here. All right. What if we've passed the whole search and the value is not there? Then there is just no value in the range which could satisfy the condition, and we are going to just return a nil from this method. All right, so we have our binary search. Let's use it in our main search matrix method. We are going to start looking for the row first. So we are executing the binary search from row number 0 to the last index row in the matrix, which is matrix count -1. And the condition checker, the check value, it's going to be the checker of the row index. So over here, first I would suggest to get the row array from the matrix. And after that, we are able to compare the values of the row array. Starting with the first one, So if the first value in the row array is greater than the target, then it means that, well, if the target could be found in the matrix, it should be looked somewhere before this exact row. So this row index is just too big. Else, let's check the opposite value in the row array. So we are going to check the row array count -1, the last one in the array, and we are going to check if it is less than target. Because if so, it means that, well, the target, if it could be found, should be looked somewhere after this row, and this row is too small. Otherwise, this is exactly the row which we are looking for, and we're going to return the OK result. All right, let's return to our guard over here. So if the row cannot be found, we are going to return false straight away. And after that, we could start work with the row values using the row index we've just found. Now we need to get the position of the target in our row array. And for that, again, we are going to use the binary search. So we are going to look from the position number 0 to a position of the last value in the array, which is row array count -1. And as for the check value, we need to provide the checker for the position index. Okay, so what we are going to check here. If the value which stands at this position is greater than the target, and, well, as the arrays are sorted, it means that the target should be looked somewhere before this one, and this index is too big. Else, let's check the opposite. So if the value is less than target, then the target should be looked after this position, and this exact position is too small. Otherwise, it is exactly the one which we are looking for, so this position index is okay. Finally, the position which we've just received is an optional integer. If it exists, then the search matrix method should return true, otherwise false. So let's just return the position is not equal to nil result. And that's it. Let's check for any compilation issues. Something over here. Oh, we forgot the dots for our cases in the switches, right? All right, here, here, and here. Nice, nice. And finally, let's submit our solution. Cool. So as you see, all the test cases passed in almost 0 milliseconds. Basically, the execution time stands somewhere on the edge of the threshold, and that's why the solution beats 100% of other submissions. And that's it for today. If you'd like to see me solving other LeetCode problems, then put your request to the comment section. See you next time. Cheers.